Everyone, welcome to this Thursday session. Let's begin on time. Our first speaker today is Xuhua He from the University of Hong Kong, who will talk to us about total positivity, combinatorics, geometry, and representation theory. Please.
Thank you very much, and it's a great pleasure to come to here and to communicate actually with you actually some of actually the topic which I studied recently and which I found quite interesting. Okay, so let's get started. The notion of the total positivity actually come back actually from the 1930s. Actually, the people actually consider about how to generalize the notions of the positive numbers to the higher dimensionals. Actually, what does this mean to talk about the positivity for the matrices? And there is actually, it was introduced by Schoenberg and later studied by Gammacher and Krem. And so a matrix, M by M matrix with the real entries is called totally positive if all the minors are positive. It's called totally non-negative if all the minors are non-negative. Well, I mean, it's quite easy actually to write down examples of the 2 by 2 totally positive matrices. So you start with these three entries which are positive, and for the first one, and you want this to be positive, and also you want the determinant to be positive. So it is very easy to solve these inequalities. But you think about if you want to do it for the 3 by 3, well, then it's not so easy. In the 1950s, Whitney and Noah, they actually proved the following result. Actually, which is very useful. So in particular, actually, if you want to write down examples of the n by n total positive matrix, and now you can easily do so by using the theorem. So, oops. Okay, so a totally non-negative matrices. Well, first of all, I mean, by the basic linear algebra, we know they actually form a monoid. They're closed under multiplication. Okay, so what are the generators? They said actually they are generated by some very simple matrices. The diagonal matrices with the positive diagonal entries, and some very simple matrices, which we call this is a xi or yi. So these are actually almost the diagonals, and with only one non-zero entry either above or below diagonal. And in the group theoretical language, this is actually the root subgroups. And so I just talk about actually what happened in the 1930s and 1950s. And a really breakthrough comes when Lusztig actually first come to study this, and he in 1994 he generalized the theory of the total positivity from the matrices to NAD groups and flag varieties, and now actually this actually becomes a very important topic. And for example, this actually motivated the theory of the cluster algebra introduced by Formy and Zalewski in 2002, and also play a key role in the higher Teichmuller theory of Falk and Goncharov in 2006. And also this is a key ingredient. So in fact, this is actually the space actually for this is the amplituhedron in the string theory studied by Arkani Hamid and Trinka. introduced in the 2014, and actually there are many more. Okay, so now let's actually come to actually more explicit examples. So we previously I mentioned actually for the 3×3, if you want to start from scratch, you want to understand the totally positive matrices, it's not so easy. But now actually, based on this structural result, now we can actually easily write down so the totally positive matrices. So we have this actually the basic blocks, the xi and the yi. And so we talk about the generators and what are the relations among these generators. Okay, so there are actually a bunch of the relations between the x and the y's and the t's. One thing we can say is that, well, the whole totally non-negative monoid, the G totally non-negative, is the product of the three terms. The total positive, total non-negative upper triangular part, the U plus part, diagonal part, the T part, and the lower triangular part, the U minus part. And a very remarkable fact is that actually for this three part, we can easily change the orders. I mean, although this matrices actually they may not actually commute, but actually this part, as I said, we can actually feel free to change the orders. This actually because we can actually easily get the relations how the U plus part commute with the U minus part and with the T part. A really interesting one is that what actually happens for the relations among the x1 and x2 in this the U plus part. And so, well, so again, so if you do the calculation, and it's very elementary, just the calculation for the 3×3 matrices. So you can easily actually check this. The x1a, x2b, x1c equals to this x2, x1, x2, and with the slightly more complicated formulas, bc over a plus c, and b over a plus c. And a key part is that, and this expression is subtraction free. We have the addition, multiplication, and divisions for these formulas, but there's no subtraction. So in particular, this is actually, if you start with the positive numbers, what you get is just the positive numbers. And in fact, this is actually one of the starting point actually for the motivations of the class algebra. Another interesting thing which I want to mention here is that if you actually forget about the actual expression, you look at, I mean, put actually this ABC and this as some star. So what you get is this is a S1, S2, S1 equal to S2, S1, S2. Well, so this is in fact the so-called Cox-2 relation or the Brito relations for the symmetrical group, and in general for the wire group, for actually Cox-2 group. And well, a different way to say this, instead of just ignoring naively what the actual number here, is that this expression holds in any semi-field. So in particular, we can think about the semi-field of one element. So this formula is a degeneration of this formula when you pass from any semi-field, or for example, from the R positive to a semi-field of one element. And okay, so this is actually what I copied from online. This is actually the Brito relation. This is actually the key relation for any Cox-2 groups. You can see we have these two different ways, change from S1, S2, S1 to S2, S1, S2. Okay, so once we have this expression, so once we actually have this is a G totally non-negative as this is as a set, and we want to understand about actually more explicitly how this looks like geometrically and topologically. For example, we want to know if they have the nice geometrical topological structures. And well, to do this, we need the stratification. So this is actually new. I mean, even for the totally positive matrices. I mean, people actually they never think about this kind of question in back to the 1930s. And so to do this, even for GON, we need this so-called the Xuhua decomposition. And well, this one actually can be actually traced back actually to the Gauss elimination method to solve the linear systems of equations. So well, we have this the Xuhua decomposition. We can write down the whole reductive G as the product of the B plus times B plus orbits, or the B minus times B plus orbits, and actually both are indexed by the variable. And so if you restrict to this U plus, and we just take this intersection, so this is a stratified space. And well, Lusztig in 1994 showed that the U plus, the totally non-negative part of the U plus, has a very nice structure. So it is a stratified space, and each strata is a semi-algebraic cell. It's isomorphic to R positive to a certain power. And moreover, the closure is given by the so-called the Xuhua orders. And so let me actually give you a simple example. So if you look at the G equal to GO2, then we have this is a U plus part, is just one dimensional. So this is the affine line. And the positive part is just the positive, the totally non-negative part of this is the non-negative real numbers. So it actually consists of the two cells, the positive numbers and 0. So the positive number, so the R positive, this is a one-dimensional cell. And 0, this is just 0-dimensional cell. And the closure relation, just you take the closure of this, you should. So this is just this one corresponds to S, and this one corresponds to 1. And this is just coincide. It's consistent with the Xuhua order. And let's actually move on from the groups to the flag varieties. And so the flag variety, again, so we start from the GOM. And so we just look at the sequence of the subspaces, the 0-dimensional, 1-dimensional, tier n-dimensionals. And this is actually called the full flag, right? Just a 0-dimensional, 1-dimensional, 2-dimensional. It looks like a flag. This is actually where this name comes from. And so this is what happens for the GOM. And so in general, so what we do is that the full flag variety is just we start from the group G, then we quotient out the fixed Borel subgroup B plus. And we can also think about the partial flag, the G quotient out, this is the PK plus. And also I want to mention this is the partial flag, the special case, which actually started quite a lot, is the so-called Grassmannians. Just you fix the dimension, you only look at this is the I-dimensional subspace in the n-dimensional total space. So this is the Grassmannian special case of the flag variety. And now the natural question to ask is what are the totally positive flag or totally non-negative flag? And so again, this is actually again introduced by Lusztig in 1994. Is that the totally non-negative flag is that you start with this is the U minus totally non-negative X and B plus. Well, this one is not closed in the whole flag, so we just take the closure. And why we actually choose this one, the U minus totally non-negative? We could also start with the G totally non-negative. But remember, the G totally non-negative is a U minus totally non-negative, then times some part in the B plus. So if you do this action, it's actually equal. So the totally non-negative flag, they actually do have the symmetry. We have the totally non-negative monoid. We're going to act on this. So it's actually stable under this axiom. And well, again, so how do we understand this? Well, one thing I want to point out is that consider the closure for the semi-algebraic varieties in general is very complicated. So it's much harder to study than the Zariski topology, because actually we need actually if you want to do this by the brute force, we really need to understand what are the boundary conditions, whether or not the boundary conditions can be achieved. When there are actually quite a lot of boundary conditions, this becomes really difficult actually to study directly. Well, so and let me actually tell you the structure for this. Well, again, we before we talk about the total non-negative part, we look at the whole space of the flag variety B, and it's a very useful decomposition. It's so-called these Richardson varieties. But in fact, I have to say that the name of the Richardson variety is somehow misleading. This was first studied by Carsten and Lusztig in the 1979 paper, where they introduced this famous the Carsten-Lusztig polynomials. Well, so anyway, so how is this defined? It's actually the intersection of the B plus orbit with the B minus. So this is actually called the Schubert cell. This is the opposite Schubert cell. You take the intersection. This is a transversal intersection. So we know this is actually always, so this is actually non-empty if and only if we have, this is a relations between the V and W by the Bohr order. And now we actually define the totally non-negative part of this Richardson variety to be the intersection of this Richardson variety with the totally non-negative. Well, a priori, this could be empty. And so actually to really to understand this, actually we really takes around 10 years. So we finally understand this in the classical setting, and so it takes more time to understand this for arbitrary Kac-Moody groups. Well, anyway, so this is actually what happened for the full flag varieties. Well, I don't want to go into the details of the partial flag, actually, because actually this is more technical. But this is, roughly speaking, this is given by the so-called projective Richardson variety. Also, this is actually quite useful and quite important when in the special case of the Grassmannians, and actually has been studied actually quite a lot. There are actually many combinatorial models actually to describe this. Okay, let me actually give you a simple example. Again, so we come back to the GO2 example, and so here again, the one group has two elements, the identity element and S, which actually changes 1 to 2. And we know the flag variety, this is P1. So P1 in the non-negative part is actually the one which, as you may expect, has the 0, the positive numbers, and infinity. So here, this index set, we have this B1s, this is the positive numbers. The B11, this is 0. And SS, this is infinity. And here you can see that again, so the Clojure relation is actually, I may expect that the Clojure of this one contains these two. And we can also see this from this index. Well, okay, so this is just for the GO2. Well, I mean, if you want to study about the GON, then it's not so easy. And well, one way actually to understand this is actually use local coordinates, but there are actually quite a lot of them. And also, it's I mean, a priori, it's not clear whether or not actually the totally non-negative part of the flag is just given by these conditions that all the local coordinates are non-negative. And well, I mean, to really understand this, we need some deep result from the representation theory. And so this is actually used the Lusztig's canonical basis. So this is actually really deep result so that we can get control of the totally non-negative part of the G and totally non-negative part of the flag variety. That's given by looking at the matrix, the matrix and the vectors associated to this element in terms of the Lusztig's canonical basis. And well, so after we actually have this, so we can actually describe this as the stratas using this so-called generalized minors for the groups and the chamber answers for the flag. So the generalized minor was actually studied by Forman and Zalevinsky, and the chamber answers by Marsh and Witch. And this actually proved by Connie Rich in 1999 for the what we call the finite, the reductive groups, and joined with Huanchen Bao from NUS. We obtained this result in 2021 for any Kac-Moody groups. That the stratas in the totally non-negative flags, they are all semi-algebraic cells. So we actually do have a nice decomposition, and the Clojure of each cell is a unit of other cell. Okay, now we want to actually move to something which I find actually really amazing. Is that okay? So now we know that actually the flag, the total non-negative flag, is a unit of the cells. But how do these cells glue together? And so people actually expect that they actually glue together in a very nice way. Actually, the best way as one may expect is that the total non-negative cell is a regular CW complex homomorphic to a closed ball. So here I just actually show you this the picture for the GO3. So from this side, we have this is a group S3. So S3 consists of the 6 elements, the 3 factorial. So the Buchar order given by this is a Hazard diagram. So we have this is the top one, this is the bottom one. We have this is the 2 of length 2, 2 of length 1. This is just the Buchar orders. And now if we actually move from this side to this side, so here you can see that you do have this is the 6 points. And if you look at one edge, this edge, so here you can see this edge. And all the other edges, you can just connect them. If you look at this from here to here, this is a rank 2, this one. And this corresponds to this point, and 2 points between, and this upper right sphere. Just something like doing the deformations for this part. And well, I mean, similarly, we can actually try to say this one corresponds to this is the up left, and this two bottom one correspond to those two bottom half part of the spheres. And well, at the end, from here to here, this three-dimensional corresponds with a three-dimensional open ball. So previously, what we have proved is that if you look down from here to here, then this is a totally positive Richardson variety. This is just the three-dimensional semi-algebraic cell, just a three-dimensional open ball. But here, this actually says more, says actually how the boundary looks like and how this group together. And so the final answer is that actually they group together and is a homomorphic to a closed ball. Well, this I mean, this actually has a long history. I mean, it has been actually studied actually for quite some time. Just list some of the major works. So first, actually by Hirsch in 2014, he proved that actually it's not the totally non-negative flag, but the links of the U plus part is homomorphic to a closed ball. And then Galashin, Karp, and Lam, they proved this for the reductive group, the flag variety of the reductive group. And finally, joined with Huanchen Bao, we actually proved this for any Kac-Moody set. And I have to say that actually our approach is actually quite different from the Galashin, Karp, and the Lam. So later, I'm going to actually to tell you a bit more about our approach, and I think that those actually has something interesting there. Not only the final result, but also I think the approach is also. Okay, so what we actually use we relies on the generalized Poincare conjecture, as we treat this as a big black box. That's actually but we also we need some really deep result from the Lie theory and representation theory, so that make sure that in the end we are able to say these cells they are go together in the way as the Poincare conjecture predicts. So what is the motivation actually to study this question? Fact actually the motivations actually from different aspects. So one actually from Lusztig. So he mentioned that a total non-negative flag is a remarkable polyhedron subspace. And so when I was a student of Lusztig, so actually this was the total positivity was actually the first problem he gave to me, and I spent that 20 years. I hope that finally I understand what remarkable means. I mean, for this setting. Later on, we're going to say that we also have many other related topics, and some cases which I know is remarkable, and some cases I expect, but I still do not know how to prove. Another actually motivation actually from the poset topology. So the Bergener in the 1984. So he showed that this is a poset, the partial order set of this Sn, and in general any Cox of the group is a shareable. So shareable is a remarkable combinatorial property. It's a bit technical, so I will not actually explain the precise definition here. But the important consequence that the shareable implies that this poset can be realized as a phase poset of a regular CW complex homomorphic to a closed ball. Well, anyway, I mean, so the question is that actually whether or not actually this regular CW complex is artificial, or is actually something come out naturally. And so this is actually a question actually asked by the honor. And for me and Shapiro in the 2000, So after they actually studied the total positivity, they conjecture that the total positivity actually provides such a synthetic Schubert varieties. So that you just this is a regular CW complex which realize the Coxeter forms. Okay, and they know that this is true. Okay, so well, I suppose actually everybody actually knows this, but let me quickly mention. So the input from the generalized Poincare conjecture is the following result: any compact, contractible, n-dimensional topological manifold whose boundary is a minus one sphere is homeomorphic to a closed ball. So if you know that the interior is the open ball, if you know the boundary is a minus one sphere, then it will be enough. This is actually the work actually of the Smell, the Friedman, and Perelman. Finally, this now is a theory. Okay, so well, the structure I want to mention, and so this is actually the thing which actually I discovered in my joint work with Huanchen is what we call this the product structure. So let me actually first actually show you this actually the final structure we have obtained. And so is that we start with the totally positive Huanchen variety, which is indexed by V and W. And we know this is a semi-algebraic cell. So this is just the product of the R positive. And so what we do here is that, well, we know this one, if you start with the element U lies between V and W, so then we know this one can be written as a product of these two. Well, I mean, if you forget about the upper part, I mean, this is a trivial statement. So this is a semi-algebraic cell of a certain dimension. These are semi-algebraic cells of certain dimension because the dimension adds up. I mean, the left-hand side and one side then coincide. So of course, we have these are isomorphic. But here the key point is that this one comes from a natural isomorphism from a really bigger space. So this isomorphism is not artificial; is a natural one coming from the full flag intersection with this open cell, and we have the similar decomposition. Well, why this actually becomes really useful? Well, so one thing is that combinatorial. This makes the study of this the Bourgeois orders between V and W to something simpler. And also, this actually tells you that how do we study the closure of this inside this open cell? I mean, so if you run over all the U's, then we understand about the whole closure. So the closure of this can be reduced to take the closure of this one inside here and the closure of this one inside. So we are able to do the inductions. So in particular, this is actually how we can understand about the closure relation, which was quite difficult actually by other method. And also, this is actually also the key part, which we show that the topological boundary of this cell is the one as we expected. Okay, let me actually show you this is the combinatorics actually behind this. Well, so well, I just copied this actually from this Nature article of the of Jody Williamson and the DeepMind team. Well, so because actually this is actually the picture which I found that has a complicated the Bourgeois intervals. And okay, so this is actually the Bourgeois interval from this element the 021435 to 240513. Okay, you can see this is actually really complicated. And if you want to study about the Wilson variety associated to this Bohr interval, you have to deal with actually all these cells from this. But if you actually pick up the U, well, I can pick up one of the U is this one. Then you can see what you have. The one part, this is just one dimensional. This is actually very simple. This actually goes back to the GO2 case, and which we have already understand. Well, this one, this part is, well, again, this is complicated, but it's less complicated than this whole point. Well, another one, and we can say just if you pick up this one. So the below don't have the two-dimensional ones. In the top, well, I just draw it by hand, so it's not looks so tidy. But I hope you can see the thing which I mean. So this Bohr interval from here to here is this part. Again, so this is it's not simple, but it's less complicated than this whole Bohr. So the upshot of this is that we can replace this whole complicated Bohr intervals by these simpler ones. And eventually, if we actually do this again and again, we can actually reduce to this one dimension. And after we reach this one dimensional, then we understand what happens. But the cost, of doing this is that we have to run through all the U's. But I mean, if you put in all the U's together, and we actually get this is a really complicated picture. And this is how we actually do this induction. Okay. So this is actually the key some of the key ingredients that we actually we introduce so that we can understand about the totally non-negative flag varieties. And there are some other basics. But actually before that, let me see. Any questions so far? Sorry, what? It's not. Well, so the decomposition comes from this one. So for this one, you just actually write down this the associated what is actually as a product of the root subgroups, and there's the way to break up this actually into this related to U. I forgot actually which order I take. So you write this as the another U plus part and the U minus part with respect to this is a little U direction, and there's two different ways to write. Either you start from the plus or start from minus, or start from minus and then ends with the plus. And each term you always take the second part. So from there is not the multiplication, but actually it's some kind of I say really interesting thing. Actually, we get this isomorphisms for this. So this was actually first introduced by Kassan and Lusztig in the paper, but probably actually not many people actually noticed that. I learned this actually from Anand Lucen. So they actually had a paper. Anand Lucen with his collaborators actually first studied this. And but now we actually find this actually quite useful to do this company. And also this kind of thing also actually appeared in this Galatian cup and lamp paper, but they actually use a different. And so, I mean, roughly speaking, actually, back to your question, I mean, each part you always take the second part. And if you want this to further intersect with another U prime, and then you have to take the second part of the second part. And I don't think that would be associated. Yeah, there's probably two cycles. Yeah. I mean, it's a very interesting question, but I haven't actually studied this before. Any other questions? Okay. So this actually happens for the fourth flag, totally non-negative fourth flag. It's actually the key ingredients which actually, and also actually has. So this we're going to combine with the generalized Poincare conjecture and combine with the Lusztig series of the canonical basis and other things. And also this combinatorial result of the Bergeron and Dyer, and putting all this together, then we actually understand about this actually for the fourth flag. We also have this result for the partial flag, but I would like to postpone this a little bit. But before that, I want to talk about this is so-called the twisted product of the flags. So it is that we can consider the n factors. And so we start with the G. So we have this B plus, we X and this G on the right, X on this left, and we form this the so-called the twisted product. And well, of course, we can naturally identify this X with n copies of the flag. But the way I want to write in this way, because I want to think about this as a stratified space. The natural stratification for here is actually different from the product. So let me illustrate this actually with one example. Again, for G equal to GO2 and N equal to 2. So previously we have talked about the total non-negative part of this of the flag. This actually corresponds to this is the closed one-dimensional interval from 0 to infinity. So if you look at the totally non-negative part of this, what we get is this the product of these two intervals, 0 to infinity and 0 to infinity. But if you consider about the twisted product, there is a natural way to define the total positivity by replacing this by all the U minus positive and look at its image taking the closure. So this one, what you get, there is actual condition. So this is a very interesting case. So what you get is just the numbers A and B, and between 0 to infinity. And the actual condition is that the A is less than 1. And here you have this AB just between 0 and infinity without any further conditions. So this one is a strictly proper subspace of this. And well, in fact, so this was actually first studied by Webster, by the Webster and Yakimov. And so, and in fact, actually for quite some time, so this was actually the only example that we know the positivity. I mean, and so so the problem is that if you start with something like this, you want to understand the closure, you pick up a sequence of the points and you want to see the limit. And if some of the coordinate goes to infinity, then you're going to affect all the other terms on the right hand side, and it becomes quite tough. Well, and now, so again, so this question actually is not only for the Kac-Moody. We can ask this question for reductive groups, but still actually it was not so easy to answer. I mean, I would say that the difficulty is almost the same. Well, and so now we I think this is also quite interesting, which I like this the so-called atlas map we introduce. Okay, so this is the way how we do this. So we start from this group G. I mean, this could be even for the GO2, or maybe I just give an example in this GO4, SO4, and we can associate what we call a cycling group. We just want to enlarge this into a Kac-Moody group. And well, you might think about this would be a crazy idea. I mean, we start with some group simple. This is a Dinkin diagram 1, 2, 3. But for the GTR, we add one vertex. And of course, this is infinity edge. For each of this is R from A1. So this actually becomes a really huge Kac-Moody group. And one may wonder why we want to do this, and even start with some simple group. So here the issue is that when you have this is the twisted copies. When we have the twisted copies, I mean, it's very hard to study this directly. The way we do is that we, instead of thinking about the X, we associate this actually to a certain sub-variety of the flag variety of this is a huge Kac-Moody. And because actually previously we have this without for any Kac-Moody, and now we can understand why, so we understand X. And so this is actually this is a preprint with Huanchen Bao. And so even if you start with a reductive group, and now we use this cycling technique to change this into a very large Kac-Moody group. So we can actually use the result there. So now we understand the total non-negative part of the twisted product of the flag variety. And we know this is always a regular CW. Yeah, I'm not sure about that. Probably we can talk afterwards. Okay, so one thing I want to mention that previously we actually have this we have this result which said regular CW complex homomorphic to a closed ball. But here we only have the regular CW complex because there is some combinatorial question which we do not know in a general case. But there are some special cases which we know. Also actually I would say one of the motivation to study the twisted product is that this includes the following as the special cases, the Brit varieties. And also this is the double flag varieties and the double Boha cells. They have the special cases. And well, I mean, we know in all these special cases, it's not only a regular CW complex, but also a CW complex homomorphic for closed. For these special cases, which we know. So in particular, we know that the length of the totally double Boha cell of a reductive group is a regular CW complex homomorphic for closed ball. And in particular, this actually solves this open problem of Fabin and Zalewinski around 2000 for the reductive groups. Okay, I have to say that actually for the double Boha cell, we are not able to handle any Kac-Moody group. We are only able to handle the reductive groups because here we have this the B plus and the B minus symmetry given by the longest element. I still expect that similar result is true for double Boha cells for any Kac-Moody group, but it's not covered by this method. Okay, so the partial flag. Well, So the idea of for the partial flag is actually similar to the thing which we discussed here for the atlas map. But here the atlas map is more difficult to explain. So for any partial flag, so for the full flag, so I do not use the black vertices. So the full flag, so the G tilde, we actually do this just as a product. And so the PK, the K, this is a subset of the simple roots associated with this the parabolic. I know this. I put this actually as the black vertices. So you can see if you have the black vertices, then the G tilde changes. There is a general rule to say how we construct the G tilde from this PK. I just show you some examples. So this actually depends on the Dinkin diagram, also depends on K. So you can see if this, for this is a SL4, and then this is a, so this is a minimum parabolic root corresponding in the middle. What we get, this is affine D4, and well, for this is this corresponds to Grassmannian, and then this corresponds to this like the diamond, and we have some different complicated ones. I mean, roughly speaking, this is just we have the way to do this is what you call this the Birkhoff of the Bohr atlas. And well, so the atlas, there's an interesting the technical part. Well, the atlas actually in this case, the atlas does not send the strata in the partial flag to the Richardson brightness. Instead, actually sends to this is the so-called J Richardson brightness. This the J corresponds to some certain subsets of the simple reflections for this larger Kac-Moody group. And so to handle the J Richardson brightness, we have to introduce this J total positivity, another technical part which I would like to skip. But the upshot is that we know this the J total positivity still behaves well. Again, this follows from product structure, and also we know this is the atlas map is actually compatible with the ordinary positivity structure on P, and this is the new total positivity on B tilde. So as a consequence, we have this regularity theorem for the partial flag, which was actually for any Kac-Moody, which was conjectured by Galashin, Kaplan, and Lan. Well, they proved this without for the partial flag for the reductive groups. They conjecture this should be true for any Kac-Moody, and now we actually prove this. And another thing is that we are able to prove this regularity theorem for the links of this U minus, and actually this actually solve this Bergeron's questions for the crystallographic causes groups. Well, this is actually another part. Let's see if I actually have the time to mention this. Let me actually quickly go through this. Another interesting thing which one can consider is that we have this natural projection map from the full flag to the partial flag. I mean, this map has been actually studied quite a lot and used to understand about the partial flags. Now we want to say how we can use this to understand about the total positivity. And this is a different approach to prove the regularity theorem for the partial flag. This is actually the very recent preprint, again joined with Huanchen Bao. So the key result is that understand about this in the fibers. We know the fibers is the unions of the cells, and we understand these cells, and there's a combinatorial property. And well, roughly speaking, this is a so-called a cyclic complete matching. Is that you look at this Xuhua intervals, you just actually find these matchings between complete matchings between all these elements. And acyclic means that after you take this, there's no cycles. So you can see that two different colors there, with the black and red. So the red one just indicates the matches. And as a consequence, we know the fibers of this are actually contractible. And again, so this actually with the other properties, the regularity property of the full flag, this is the thing we need. And this would imply the regularity for the partial flag. Well, this approach actually, so we can bypass this complicated the J total positive and atlas map. And another interesting is that so that we actually, as a byproduct of studying this, we are also able to confirm another conjecture of Lusztig, is that the totally non-negative sprinkle fiber. Okay, so let me actually give you a summary. Is that actually so the total positivity? I think this is actually something which is interested me quite a lot. It actually combines the representation theory with the geometry and with the combinatorics. And you can see all this has to be put together. The intersection of this actually I find is quite interesting. Well, besides the thing which I have mentioned, there are actually also many other related topics I also think quite interesting. So far I talk about the split groups, and also we can study about the theta positivity for the notion of theta positivity for the non-split groups, and also it's actually motivated from the high Teichmuller theory. And I would expect that this might be related to this is a generalization of Lusztig canonical basis for the I-canonical basis introduced by Huanchen Bao and others. And also the double flag variety, I would expect this to be related to the tensor product of the canonical basis. And also this is a amplituhedron. So this is also from the string theory. I mean, this is another really amazing area. And also we can look at this the tropical version of the total positivity. And this is in general the total positivity over any semi-field. And also the thing which is actually related to the clusters and many others. Yeah, I will stop here. Thank you very much.
We have time for a few questions.
Subvariety. When you embed in this larger group, you have a certain subvariety of the big group. So what geometrical properties allow you to?
So when you do this embedding, so yes, and also actually how to find this, how we find this, we first actually done this at the levels of the Coxeter groups. So yeah, we start with well for the partial flag we still have these pairs of the elements V and W, and then we want to cook up a larger element for a single element in the Coxeter group of this larger Kac-Moody group. And so this actually Richardson and projected Richardson into the Schubert cells, into part of the Schubert cells.
Is the power of the Bao group embedded in the Bao group? No.
Yes, the pairs. And the special case of this you can see easily. So the pairs of this V and W, there's no relation. So this just corresponds to the element V and W, because here we have the product. This is a trivial example. So this the V and W as a pair index the Richardson corresponds to the Schubert set here. But actually in the others we become more. Yes. Oh, you mean this is the twist product?
Yeah.
Twist product, you start from here. You have this is the W1, W2, W3. And what you get here, this is the W1, S infinity, W2, and so on. No, they don't want them to commute. This is the reason we want to introduce this infinity. Because here we don't want them to commute. We want to put some extra thing so that make sure that they never commute. This is the trick here. Yeah.
More questions?
First questions about positive Schubert calculus. Do you know Schubert classes, positive analog of Schubert classes, and corresponding polynomials and extension of this theory for K theory?
This is actually a very good question. I know that.
Don't speak.
Oh, sorry. Yeah. So yeah, I know there's a total. There's a various of the positivities related to the Schubert calculus, the K series. I mean the cohomology. But I do not know. I mean, if there's any direct relations with Lusztig positivity.
Sorry, another question is the total positivity is a special class of matrices, the so-called Carvin matrices, when you consider all family of matrices such that all K minus of these matrices have a fixed sign. For example, there is very famous class of Hodge matrices. Hodge matrices. Do you know something about extension of Lusztig work for other classes of Carvin's matrices?
I do not know, but this is certainly a very interesting question. Probably we can talk afterwards. Yeah, I would like to talk to you afterwards and to know more about it.
Okay, we have time for one question.
Actually, at the end, you said something about the tensor of canonical basis. Can you, in this study, I mean, say something more?
This page?
Yeah.
Well, I mean, certainly actually the double flag with the tensor product of canonical basis, actually, we actually do have some small examples which we say that there must be a close connection. And we are also actually working on this actually with some of my postdocs. And for the I-canonical basis, we have some calculation for SO2. That's actually also sounds interesting, but actually from this, I mean, I think actually there's still a long way to go. I mean, whether or not actually we can actually relate the I-canonical basis with the setup positivity. I think that is still a long way to go.
I suggest we take future questions to the coffee break, and let's thank our speaker again.